So this is the beginning of the end of lecture 4 on acids and bases based upon chapter 15. And in this video we're going to learn how to calculate pH, pOH, the concentration of H plus as well as the concentration of OH minus. So the key thing to remember is that water does autoionize. Although it is happening on a very tiny scale, this equation represents the autoionization of water, where one water molecule acts as an acid, the other one acts as a base. The one that acts as an acid donates a proton and becomes OH minus. The other one that acts as a base accepts a proton and becomes H3O plus. This is the autoionization of water. Now this doesn't happen very much in pure water. There's actually very little of this H3O plus and OH minus ions in solution. In terms of the actual concentration, for both of these molecules, there's only 1 times 10 to the minus 7 moles per liter. This number, if you write it, is 0.0000001. There's actually very little of these molecules or these ions in solution in pure water. Okay. However, it is important because the amount of H3O plus and OH minus in solution is used to calculate the Kw, which is the ion product constant. The Kw is the one variable we should pick up in this chapter. Okay. And it is the product, so it means that you multiply the concentration of the two ions, the H3O plus ion and the OH minus ion. That's why it's called the ion product constant. Okay? And since we know that both of these concentrations equal 1 times 10 to the minus 7, Kw always equals 1 times 10 to the minus 14. I would write this equation down here, what Kw equals, and I would write down this number here in terms of what is Kw, because it is a constant. All right. Now Kw is actually the ion product constant, but it is not a new variable per se, in that it is derived from Kc. So if you look at the autoionization equation for water, we say that these are the products, okay, and these two water molecules are the reactants. Okay. So if you were to write a Kc expression, you would say Kc is equal to the products. The products is the concentration of the H3O plus and the OH minus, divided by the reactants, which is just 2 waters, so H2O squared, because there are 2 water molecules. Okay, and remember that the water is a solvent. Okay, so not only is it a reactant, but it is also the solvent, so it is in great excess, very, very great excess, because it's the solvent. Okay, remember from the lab, when you have something that is in great excess, its concentration does not change much. And the reason its concentration doesn't change much is because even though some of it reacts, it is in great excess. Okay, therefore it is what we call a constant. Okay, constant value. Okay, so if that is the case, okay, let's move the water over to the other side. So we're going to multiply the right side by H2O squared, and we're going to multiply the left side by the same thing. Okay, this cancels out the denominator. Okay, so we say that we say that H2O, the concentration squared, times Kc is equal to the H3O plus concentration times the OH minus concentration. Okay, remember H2O is a constant because it is the solvent and in great excess. Kc is a constant because it is the equilibrium constant. So a constant times a constant, we're going to call this new constant Kw. Okay, and so therefore Kw is equal to the H3O plus concentration times the OH minus concentration. Okay, so really Kw is really derived from Kc and not a new variable per se, but also an equilibrium expression constant. Now in terms of the autoionization of water and those two equations that we were looking at, Kw can be used to solve for the concentration of acid or base, depending on what is in the solution. Okay, so let's say you have a strong acid and you have 0.1 moles of HCl. Remember, when you have a strong acid, there's a full dissociation, which means you really have 0.10 moles of H plus in solution, as well as 0.10 moles of the Cl minus in solution. Now, the Cl minus doesn't really affect the pH, but your H plus in this case will affect the pH of the solution. Okay, so because we are in 1 liter, we have 0.10 moles per liter, or 0.10 molar H3O plus concentration. Okay, if we rearrange the equation here, we say that OH minus is equal to 1 times 10 to the minus 14 divided by 0.1, and so we get 1 times 10 to the minus 13 as the OH minus concentration. Okay, if you have a strong base, say 0.10 moles of NaOH, remember again, NaOH is a strong base, and so it fully disassociates in water, so you have 0.010 moles of Na plus, as well as 0.010 mole of the OH minus. Okay, now the Na plus again doesn't affect the pH, but the OH minus will. So really, since in 1 liter you have 0.010 mole per liter or molar of the OH minus, plugging that into the equation and solving for H3O plus, you get that the H3O plus concentration is 1 times 10 to the minus 12. Okay, so let's look at it. If you have a H3O concentration of 1 times 10 to the minus 12, this means that the H3O plus concentration is less than the 1 times 10 to the minus 7. Therefore, it is this case here. This is a basic solution. Okay. If you're looking at the first situation, okay, and you're saying the H plus concentration is given to you as 1 times 1.0 or 1 times 10 to the minus 1, okay, then that is this situation here where you have H3O plus is greater than 10 to the minus 7. So this is an acidic solution. And this makes sense, right? Because you have HCl in the first example and NaOH in the second example. So HCl should give you an acid solution and NaOH should give you a basic solution. What does this really mean? This really means that if you have H plus equal to OH minus, the solution is neutral. We know this for a fact. For example, if you have just water, when we talked about this, the concentration of the H plus is equal to the concentration of the OH minus is equal to 1 times 10 to the minus 7, right? So that's a neutral situation where they're equal to one another. So that would be this situation here. If the H plus concentration is greater than the OH minus concentration, it would be here. And if it's less than the OH minus concentration, it would be here, which is basic. But in all cases, remember Kw should equal 1 times 10 to the minus 14. All right. So based on this equation, Kw equals the H plus concentration times the OH minus concentration. We can solve for either H plus or H minus concentration depending on what we were given, right? So let's look at the first situation. You have 1 times 10 to the minus 9 is your OH minus concentration. So really we're going to rearrange the Kw equation to say that the, sorry about that, give me a second. We're going to rearrange the Kw equation, say H plus is equal to, and we're going to divide both sides by OH minus, so we get Kw divided by OH minus. Okay. Using this equation, we can then solve for the H plus concentration. Kw is 1 times 10 to the minus 14. OH minus is 1 times 10 to the minus 9. And so 10 to the minus 14 divided by 10 to the minus 9 is 14 minus a minus 9, or 10 to the minus 5. Okay. In the second equation, we're given H plus instead of OH minus, but we can rearrange this to say OH minus is equal to Kw over the H plus concentration. So really, 1 times 10 to the minus 14 divided by 2.6 times 10 to the minus 8. Okay, this comes out to 3.9 times 10 to the minus 7 molar. This is the H plus concentration. This is the OH minus concentration. Last but not least, you have iron hydroxide. And remember, because this is a subscript 2, there's actually 2 hydroxides for every molecule of iron hydroxide. So really, if you dissolve this in water, you're going to get 1 Fe and 2 OH minuses, right? So therefore, the OH minus concentration is actually equal to 2 times 0.035 or 0.070 molar, okay? Then we're going to reuse our first equation. H plus is equal to Kw over the OH minus concentration, okay? So 1 times 10 to the minus 14 divided by 0.070. This comes out to 1.4 times 10 to the minus 13 molar. And again, this is your H plus concentration, okay? So again, we're going to assign acidic or basic or neutral, okay? So we're looking at our H plus concentration only, okay? So in the first one, the H plus concentration is 1 times 10 to the minus 5. So therefore, it is greater than minus 7. So it is the first situation there, right here, okay? So therefore, it is going to be acidic, okay? The second one, we can't look at this OH minus concentration because that's not what we're looking at. We're looking at the H plus concentration, which is what is given to you, okay? And so based upon this, 2.6 times 10 to the minus 8. Minus 8 is less than minus 7. So it's this last situation here. So it is basic, okay? And we're looking at the last one, 1.4 times 10 to the minus 13. Minus 13 is definitely less than minus 7. So again, it is basic. All right. Now, a lot of times rather than calculating using Kw, we often calculate using something called pH, okay? And so really the acidity or basicity is reported as pH is equal to negative log of the H plus concentration. pOH is equal to negative log of the OH minus concentration, and therefore pH plus pOH is equal to 14, okay? pH stands for the power of hydronium, or how much H3O plus is in solution. pOH stands for the power of hydroxide, or how much OH minus is in solution. And the pH scale will run from 0 to 14 because Kw is 1 times 10 to the minus 14. And it is neutral at 7 because when you have a neutral solution like pure water, the H3O plus concentration equals the OH minus concentration equals 10 to the minus 7. Okay, so a lot of times we have these things in our textbooks where they tell you the pH of various solutions, like baking soda here is a little bit basic. We got vinegar, it's a little bit acidic. Beer is a little bit acidic, okay, so on and so forth, okay. The idea in this video, or the main idea, or the main concept, is to be able to, if you're given a pH, determine the pOH, the H plus concentration, and the OH minus concentration. So what I find very, very helpful is this little chart here that I put together, okay. And I would pause the video and draw this or write this down, because if you need to go from pH to pOH, you go 14 minus pH. Just follow the arrow. If you need to go from pOH to pH, you just go 14 minus pOH, so on and so forth. Okay? And we're going to use this in terms of the problems that we're going to do. So let's look at an example. Okay? It says a sample of orange juice has a hydronium ion concentration. So this is your H3O plus concentration of 2.90 times 10 to the minus 4. They would like to know what is the pH and is the solution acidic or not. Okay, so let's look at how we would do this kind of problem. We would say we are solving for pH, and we're given the H3O plus concentration or the H plus concentration. So we're going from H plus, and we're trying to get to pH. Okay, so we're just going to follow this arrow here in this direction. Okay, and we're going to say pH is equal to negative log of the H plus concentration. Okay, so therefore it's equal to negative log of 2.90 times 10 to the minus 4. So that comes out to, didn't write that down. We'll just do it real quick. Negative log of 2.9 times 10 to the minus 4. This comes out to 3.54. Okay. Now remember, with the pH situation, okay, we're going to just slide ourselves up a little bit, okay. It is neutral at 7, okay, but, so neutral here is at 7, okay. Anything basic is up to 14, so 7 to 14 is basic, okay, and 7 to 0, 0 to 7 is acidic, okay. So therefore, 3.54 falls in between 0 and 7, so it is acid or acidic. Okay. Let's look at another problem, a saturated solution of calcium hydroxide. Be careful, calcium is from group 2 is 2 plus, hydroxide is OH minus, so you need two OH minuses, or because calcium hydroxide is CaOH2. Okay. So therefore, when you dissolve it in solution, you're going to have to double the concentration, okay? So it has a hydroxide ion concentration of, I'm sorry, I take it back. They tell you the hydroxide ion concentration is this, okay? So then you don't need to double it because that is the hydroxide ion concentration. So the OH minus concentration is 0.0250, okay? Be careful. If the wording had said that you had a solution of 0.0250 calcium hydroxide, okay, then you would need to double the concentration of OH minus, okay? But since it says here a hydroxide ion concentration, then you don't need to double it. So be careful in terms of the wording, okay? So they're asking you what is the pH. So the easiest way, I think, is to solve for the pOH first. Okay, the pOH is equal to, and we have the OH minus concentration. So we have the OH minus concentration. We're solving for pOH, so we're going in this direction. So we're going to go negative log of the OH minus concentration, which is negative log of 0.0250. Okay. So if you do the math on this, this comes out to 1.60. Okay. Now that's not the end. They're asking for the pH. So I have the pOH. I want the pH. So I need to follow this arrow here. 14 minus pOH. So pH is equal to 14 minus pOH, or 1.60. This comes out to 12.4 as my pH, okay? And since the pH is between 7 and 14, it is basic, okay? Let's do a couple more examples, okay? You say a brand of carbonated beverage has a pH of 3.16. What is the hydronium ion concentration? So they say that the pH is equal to 3.16, and they would like to know what is the hydronium ion. So they want us to know what is the H3O plus concentration. Okay. So again, we're just going to go ahead and use our little table. So we want to know the H3O plus concentration given the pH. So we're going to scroll ourselves up real quick. Okay. And we're looking at this situation here where we have the, let's erase some of this stuff so it becomes clear. We have the pH, and we would like to know the H plus concentration. So we're going to go in this direction here. So we're going to use the equation 10 to the minus pH. Okay, so therefore we would say that the H3O plus concentration, okay, is equal to 10 to the minus pH, okay, or 10 to the minus 3.16. So if you do that in your calculator, the H3O plus concentration should equal do that real quick on my calculator. 10 to the minus 3.16, 6.92 times 10 to the minus 4 molar. Okay. On the homework, when you're writing these concentrations, please don't forget to write the unit of moles per liter or molar. Okay. Last question. If you have a 0.01 molar solution of ammonia and it has a pH of 10.6, okay, so the pH is given to you as 10.6, okay. What is the concentration of the hydroxide? They would like to know what is the OH minus concentration, okay. So one way to solve this problem is to first find the pOH, because the pOH is equal to 14 minus pH, okay. And again, that's from the little table that we were using up there. So 14 minus 10.6 is equal to 3.4. Okay, that's the pOH. Okay, so we would like to find the OH minus concentration. Okay, again, that is equal to, so you have the pOH, you would like to find the OH minus concentration. So let's scroll up. If you have pOH, oops. Okay. And you would like to find the OH minus concentration, you're using this arrow here, 10 to the minus pOH. So therefore, we're going to do that. We're going to go, the OH minus concentration is equal to 10 to the minus, oops, this is the wrong problem. I need to scroll further. Is equal to 10 to the minus 3.4. And therefore, if you plug that into your calculator, you should get 3.98 times 10 to the minus 4 molar. Okay. So hopefully that will give you, those 4 problems will give you an idea of how to use each of those equations and the little table that I gave for you up there. All right. The last little bit in terms of the slides is just a little background. Okay. The idea of pH and pOH was actually developed by a Danish biochemist by the name of S.P.L. Sorensen. And he actually was working in a beer brewing factory. And so part of the job of all of the workers is to check on the level of fermentation. And they do it by measuring the acidity. Remember, beer is slightly acidic. So they know that they have the beer has fermented enough, there's enough alcohol in it by measuring the acidity. So he was frustrated, and the reason is because he was working with these power of 10s, like 3.5 times 10 to the minus 15 times 10 to the minus 7. And so he had to work with numbers instead of kind of acidic, more acidic, okay? And so he developed the pH scale in order to work with actual numbers, so like 3.5 or 6.8, actual numbers instead of power of 10s, so to make things a little bit easier. Okay, so in this beer brewing factory, they implemented this pH scale, and now it's prevalent and worldwide, and we use the pH to measure all kinds of things. Like, for example, if you give a urine sample, oftentimes they'll measure the pH of that with a little dipstick. And so it all started actually with one guy and trying to brew beer. I think it's a fun story to learn a little history, as well as see how things are oftentimes developed by necessity. Now, the way to measure pH is a couple of ways, okay? The more cost-effective way are these indicator dyes or strips. These dyes or strips have these chemicals embedded in them, and the chemical is pH sensitive and will change different colors depending on what pH it's in. And so you just dip the little pH strip into the solution, and it will turn, usually it'll turn pink or red when it's acidic, and it'll turn green or blue if it's basic, depending on who's making these strips. The strips are less precise and not reusable, so once you dip it in, you gotta get a new strip. You can't reuse that same strip. But it's very good for things like if you're out in the field, you're measuring the pH of various bodies of water or small volumes, or if you're in lab, you're just doing an experiment and you just want to know, is my experiment done? Or if you're dealing with noxious samples, really toxic or oxidative or reductive samples, then it's oftentimes best not to stick a metal probe into your sample. So therefore, these are the more cost-effective and cheaper way to take pH. There is something called a pH meter, and I'm sure we've all used this in lab. Okay, it is much more accurate, gives you decimal points after the whole number. It is much more expensive in terms of cost. There's an electrode that's a probe, and the electrode measures the H plus concentration. It does need to be standardized and calibrated every time before use. And of course, it often will need a source of electricity or a battery. Oftentimes, these are used in the labs. People don't, well, sometimes they do, but people don't often carry sophisticated pH meters with them in terms of going out into the field. So there are different kinds of indicators. Also, indicators are used in titrations in lab. And so indicators actually change color in various amounts of pH, and they don't always change color at that pH is equal to 7 situation. Phenolphthalein, which is the common one, we used phenolphthalein in another one of our kinetics labs, actually changes from pink to colorless at around 8 to 10, okay? Now, if you were studying the pH of something else, let's say at pH 4, right, you wouldn't use phenolphthalein because seeing the change at pH 4, you would see no color change. At pH 4, it's colorless. At pH 5, it's still colorless. So choosing phenolphthalein, if you're looking at a reaction where the neutralization happens at pH 4, is not very helpful. In this particular case, you would choose something where it changes color, so you would choose one of these ones, right? You could choose bromophenol blue or methyl orange or bromocresol green, because these ones actually change color at the pH you're interested in, okay? So in lab, there is a post-lab question that will ask you to pick the correct indicator. You will have to use this chart to be able to decide what is the correct indicator for your particular experiment, okay? And there are all kinds of nice little handy charts like this. For example, if you're looking at phenolphthalein, right? It's colorless at 1, colorless at 2, colorless at 3, 4, 5, 6. It doesn't actually change into the nice pink color until pH 9, right? There are other indicators that change multiple colors. For example, there's something called the universal indicator, and it is that because at pH 1 through 4, it's about orange, and then it changes to yellow at around pH 6, and then it changes to like a teal blue color at pH 8, and then it changes to purple at the 10 to 11 range. So the universal indicator covers a range of pHs. That's why it's the universal indicator. Of course, these indicators have different costs associated with them, so obviously it's more not cost effective to use the universal indicator every single time. And that's why phenolphthalein, which is fairly cheap, is used in a lot of undergraduate labs. Okay. The last slide I wanted to go over was this idea of log in terms of calculating pH. Okay. Now it seems like the difference between 1 and 3 seems very small. So you may think, the difference between pH 1 and pH 3 is not that much, not a big deal. Okay. But actually, the difference between 1 and 3 in terms of pH is the difference between 10 to the power of 1 and 10 to the power of 3. So the difference is actually much larger because it is the difference between 10, which is 10 to the 1, and 1,000, which is 10 to the 3. Okay? And the reason is this. pH is on a log scale. Okay? The difference between pH 1 and 3 is really the difference of the H plus concentration. Now remember, log works like this. If you have 2 times 2 times 2, that's equal to 8, right? So you have 3 2's multiplied together. Really, that's saying log base 2 of 8 is equal to 3. Okay? That's the definition of what log is, right? Your 2 becomes your base, and your 8 becomes your what you put inside, and your 3 is how many of the 2's you have, right? So with our scale in terms of acid and bases, it's actually a log base 10. Okay, so really, oftentimes the base 10, the little 10 is dropped for convenience, but it really is there. It's a base 10 situation. That's why when we go from pH equals negative log of the H plus concentration, right? When we say that H plus is equal to 10 to the minus pH, why do we use 10? Is because it's a log base 10, right? So really, negative log base 10 of 1 times 10 to the minus 1 is 1. So the H plus concentration is 0.1. But log base 10 of 1 times 10 to the minus 3 is 3. So really, the H plus concentration is 10 to the minus 3, or 0.001 molar. See? 1 and 3 is a huge difference, right? In terms of the concentrations, right? If you're comparing these two numbers, this really means that there is 100 times more ions of H plus in the pH 1 solution versus the pH 3 solution, okay? So it's a huge, huge difference. And in fact, in biology, the difference between, let's say, your normal body pH is like 7 I think it's like 7.3 or 7.4, okay? If you have a pH and your pH in your body falls to like 7.1 or 7, or it goes up to like 7.8 or 9, you can actually get really, really sick because of this situation here that we're talking about, where we're saying it's a huge difference between 7 and 8 in terms of the pH, right? It's a tenfold difference. If you have 10 times more H plus concentration in your bloodstream than you should, than is normal, of course you're going to get very, very, very sick in terms of like vomiting and nausea and fainting and stuff. So really, it's very important to recognize that although it doesn't seem like a huge difference between 1 and 3, it actually is a big difference, because it's really the difference between 10 and 1,000, right? If I owed you $1,000 and paid you back $10, you would not be okay with it, right? So anyway, that's kind of just for explanation of why it seems like a small difference, but it's actually not a small difference. All right, that ends this video on lecture 4 part 4. This is the last video, so you should go ahead, if you haven't done so already, and finish the homework for chapter 15 on acids and bases, and get that turned in, and then of course take the online quiz on Canvas. All right, have a great week.